Okay, let's cover the new stuff real quick, then we can get to the test. So the new topic that we're covering today is lists. Now, what is a list? It's an ordered sequence of objects. Have we covered sets in this class? We haven't covered a set before? Okay. So we don't have that to counter it with yet. We'll come across sets later, so forget that. It's an ordered sequence of objects, and we use parentheses to signify it. You're used to lists. You've used them 100 times. Every time you've talked about like a point in the xy plane, you did its x-coordinate and its y-coordinate, and you put them together in parentheses to make a list. If you were to do a point in three-dimensional space, x, y, z, you'd use a list for that. All we're saying is that it's a collection of three things, namely the numbers 1, 2, and 3, in that order. It's an ordered collection of objects. You can put anything you want in the list. So here's a list. What's inside the list? The first object in the list is the set containing 1, 2, and 3. The second object in the list is SpongeBob. The third object in the list is all integers. And the fourth object in the list is Bob. So there's a list. There's only 4 things in it. Perfectly valid list. And it's in particular order. That's the first thing in the list. That's the second thing in the list. That's the third thing in the list. That's the fourth thing in the list. Make sense? So you just do parenthesis, put an object in, comma, put another object in, comma, put another object in until you have everything in that you want, and parenthesis. There's an object, there's a list with 3 things in there. Let's do one more to check our intuition. How many objects are in that list?
2.
Only 2. What's the first object in the list? The list containing 1, 2. What's the second object in the list? 3. Okay, good. So, lists, there's some examples of lists. When we have a list, x, y, z, this list is equal to the list a, b, c, if and only if x is equal to a, y is equal to b, and z is equal to c. If you feel like I just keep saying the same thing over and over again, good, you're getting it. Okay? Make sense? All right, so let's see that in action. Is the list 1, 2 equal to the list 2, 1? No, because 1's not equal to 2 and 2's not equal to 1. Is the list 1, 2, 2 equal to the list 1, 2? No, they're not even the same size. We can't even compare all the objects because we have nothing to compare that to. Okay. So, one of the big topics we're going to cover in this class, and it's going to come up over and over again, is counting. And I know you all think you know how to count, but we'll put that to the test. So oftentimes we're going to want to count things. A common object we want to count is lists of things. We want to count how many ways we can list things. So here's a common example. How many 2-element lists can we make from the numbers 1, 2, 3, and 4? How many lists can we make where the only elements in the list are 1, 2, 3, and 4? We can only use 2 elements. 16. Here they all are. You can have the list 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, blah, blah, blah. And you see, there they all are. Can you think of any other 2-element list I could make with the numbers 1, 2, 3, and 4? No. So it's pretty intuitive that there's 16. One way you could have thought about that is, well, I have 4 options for the first element, and I have 4 options for the second element. Therefore, I have 4 times 4, 16 total options. Make sense? Trying to appeal to intuition? All right, so let's ask a more general question instead of using a particular number. Let's just talk about some number, n. What number? We don't know, n. How many 2-element lists can I make with n options for each element? So if I have n options for the first element and n options for the second element, how many lists can I make total? N times n. I have n options for the first element. I have 1, 2, 3, 4, 5, 6, 7, all the way up to n. What's n? It's just some positive number. It could be 10, could be 50, could be 19. What we're trying to do is come up with a formula so that you know how to count no matter what n is. Right? So, we have n options for the first element. We have n options for the second element. So we have n rows with n elements in each row, or n times n, or n squared. However helps you think about rows. Another way you can think about it is like counting the area of the sink. If we think about each one of these as a 1 by 1 block, that's another way to do it. I don't know, whatever helps your intuition. So you know what, there's n squared lists here, right? Okay, question. What if I get rid of all the lists with repeating elements? So I pull out 1, 1, I pull out 2, 2, I pull out 3, 3, 4, 4, 5, 5, 6, 6, 7, 7. Pull out all those. How many do I have left?
N squared minus n.
N squared minus n, perfect. N squared minus n. Notice that there's n elements with repeating elements. There's 1, 2, 3, 4, 5, 6, 7, all the way up to n elements with repeating elements. N lists with repeating elements. There we go. That's perfect. So does it make sense that the answer is n squared minus n? Another way you can think about it is, if I were to get rid of the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, then now each row only has n minus 1 elements, right? So now it's n minus 1 times n. So n times n minus 1, you'll notice that's the same thing as n squared minus n. So what she said was perfectly valid. Her way of thinking about it, I assume, was thinking about n squared now minus the row, which has n, or minus the diagonal, which has n list. Or you could have thought about it, okay, now we have n rows, and each row now has n minus 1 elements. Those are both perfectly valid ways of thinking about it. When it comes to counting problems, one of the hardest things to do is to come up with a way of thinking about the problem that appeals to your own intuition. So it's possible for me and you to count in very different ways and still come at the exact same answer. Like I counted this way, Emma counted that way. We came to the exact same answer, but we thought about 2 different ways. Now this is a real simple example, but as we get to more complex counting problems, you're going to notice that one of the hardest parts is just coming up with that way of thinking about it that just appeals to your intuition. And there's no trick to doing it. You just got to keep thinking about it until you think of a way that, oh, that makes sense. Or, oh yeah, that is what that's counting. So we'll see more complex examples, but yeah, both those are perfectly valid ways of thinking about that. So what about without repeats? We answer that question. Okay, so now let's change our picture. Let's say that we had n options for the first element, but we only had m options for the second element. Do you understand what I'm saying? So an example might be, how many lists could we make? Do an example over here. In the space where I can sit down, right? So let's say that for the first element, I say you can use the numbers 1, 2, and 3. And for the second element, you can only use the numbers 1 and 2. How many lists could I make? I can make 1, 1. I can make 1, 2. These are all the ones I can make starting with 1, right? My first element has to come from here. This is where my first element has to come from. And my second element has to come from here. My second element has to be one of these. So these are all the ones I can start with 1. Oops. These are all the ones I can start with 2. And these are all the ones I can start with 3. So there's 6. 2 times 3 is 6. Total options, right? That's what we're saying in this chart. This is, we have n options for the first element, so this is counting 1, 2, 3, 4, 5, all the way to n, whatever it was. In this case, n happened to be 3. And then we have m options for the second element, count to whatever it was. In this case, n happened to be 2. Then there was a total of how many? Yeah, but now in this picture, n times n, because we have n rows and we have m elements in each row. So we're doing m plus m plus m plus m plus m n times, or n times n. Is this appealing to everyone's intuition? Okay, wonderful. So now we're going to do a quick proof that that's the case. And the proof is just going to rely on the exact intuition that we just established. Now you're going to notice with counting proofs, and that's what these are called, counting proofs. For those of you who are used to rigorous proofs, you're going to feel like that didn't really prove anything. You're just using intuition. And that's the way that counting proofs feel in the beginning. So it's one of those types of proofs that You just got to do a bunch of them to get used to them. So it's going to feel weird to begin with. I remember the feeling. I just can't remember why it felt so weird. So if it feels that way, that's kind of to be expected. So let's do the proof real quick. And the proof's also in the book, by the way, of all the things I do in class for the most part. Usually I'll do it somewhat different from the author, just because he and I don't think the exact same way, but anyways. So consider all the two-element lists for which there are n choices for the first element, and for each choice of the first element, there are n choices for the second. That's exactly what we were saying, right? Then the number of such lists is n times n. Exactly what we expected from that picture there.
That's a proof.
No, that's the words, and then it continues up there.
Oh. That's not a proof.
So consider a chart. Now you'll notice chart's not a well-defined term. I'm assuming that you understand what I mean by chart. Consider a chart of your list such that each row in your chart contains all the lists that begin with a particular element. So this row in your chart contains all the lists that start with a particular element, namely 1. This row in your chart contains all the elements that start with a particular, or all the lists that start with a particular element, namely 2, etc. You see how each row that we've drawn in this picture, every list starts with the same element? That's what I'm saying here. Construct a chart of your list such that each row in your chart contains all the lists that begin with a particular element. Since there are n options for the first element, there's going to be a total of n rows. Since for each choice of the first element, there are m choices for the second element, then each row contains m lists. Make sense? Therefore, there are n rows of m lists, or there are n times n total lists. Right? Basically just putting on paper all the explanation I did in explaining this picture. So sometimes we'll have, a lot of the times when we're doing a counting proof, we'll have a picture in our heads of how we're counting that makes sense, and then we're trying to put it in words. Sometimes if people aren't familiar with counting proofs, it's hard for them to know the picture that you're talking about, which is why I explicitly drew the picture I'm talking about for you guys, and then explained it there. But that's common with counting proofs, that they're just explaining a picture, and if you're not already familiar with those types of pictures, it might be hard for you to understand exactly what they're saying. So we good with that? Yeah? Oh yeah. Okay. Then let's move on. All right. Let's do some examples of counting. So let's say that we view a person's initials as a two-element list. We're going to ignore middle names. You have first name, last name. We're going to view your initials as a two-element list where we take the first letter from your first name and last name. How many possible lists of initials can we make?
30.
So I could make AA. That's a possible list of initials.
Oh,
I
so
can make
all
AB.
the letters in the alphabet?
Yeah, you can use all the letters in the alphabet.
26 squared. 26 times. So whatever that is.
26 what?
Squared.
26 squared. Now this is a great example of the type of thing I don't want you to do on your test. If the answer is 26 squared, write 26 squared. Don't do some scratch work off to the side to calculate what 26 squared is and then put that as your answer, because I have no clue where that number came from. See, 26 squared, I understand that you're counting 26 for the first, 26 for the second. I understand you're thinking perfectly. That's right. Here, we're not interested in, do you know how to multiply numbers together? We're interested in, did you know how to count them? If you put 26 squared, it's very clear to me that you knew how to count them. Okay? And then how many if we don't allow duplicate initials? So you can't have AA or BB or CC or DD.
26 squared, subtract 26.
Or 26 times 25. Both those answers, perfectly good answers. And you don't need to calculate them, and I'll understand exactly how you did it. Right?
Mm-hmm.
Okay, wonderful. Let's do another one. One that's more interesting. So there's 7 of us in this room. Now there's 8 of us. Now there's 7. That was weird. Tricked my brain for a second. Thought I didn't count myself when I did. Alright, anyways. There's 7 of us in this room. Let's say that we decide to elect a president of the room and a vice president of the room. How many ways could we do that? How many options are there for the president?
7.
There's 7 options for the president, right? And then, once we choose a president,
There's 6.
that person can't be the vice president as well. So there's 7 options for the president and 6 options for the vice president for a total of 42 options, right? 7 times 6. That's how many ways in this room we could elect a president and vice president. Make sense? So, a club has 10 members. How many ways to elect a president and a vice president? 90. There's 10 options for the president. Now we've chosen someone to be the president, so now there's only 9 people left over that we have to choose from for the vice president. Make sense? 10 times 9 ways that we can do that, we're 90. Alright? Another question. How many 3-element lists can we make using the numbers 1, 2, 3, 4, 5?
125 or 5 cubed.
5 cubed, 125, right? We have, if we're talking about filling out some random list, we have 5 options for the first element, 5 options for the second, 5 options for the third. We have 5 options for the first, and for each of those 5 options, we have 5 options for the second, and for each of those 25 options, we have 5 options for the third. Make sense? So for a total of 125 ways to do that. You're learning how to count. Wonderful. Next. A club has 10 people. How many ways to elect a president, a vice president, secretary, and treasurer?
10 times 9 times 8 times 7.
Yeah, don't hurt yourself. 10 times 9 times 8 times 7. Whatever it is. 10 times 9 times 8 times 7. That number is the number of ways that we could do that election. Right? So you're starting to notice a pattern. You're starting to notice if we allow repeats, so I had 5 options for this one, 5 options for this one, 5 options for this one. It's however many options I had to the power of however many times I'm doing that choice. Down here, you notice it's however many I have times 1 less times 2 less, and you keep following that pattern until we've done it for however many times we need to do it, our k choices. Right? So let's put that in writing now. Let's write that out explicitly. So what we're saying is when we allow repeats, then if there's k choices, then it's going to be n times n times n times n k times, or n to the k choices. When you don't allow repeats, it's going to be n times n minus 1 times n minus 2, all the way down to n minus k plus 1. If k is the number of choices you're making. So for example, up here, we said it was 10 times 9 times 8 times 7, right? Which is the same thing as if 10, we plug in for n, and what's k? 4. K is how many choices we're making, and n is how many options we have for each choice. Right? So plug in n and k to this equation, what do you get? Plug in 10 for n, you get 10. Plug in 10 for n, you get 9. Plug in 10 for n, you get 8. And you keep on going, clear until you get to whatever this number is. Plug in 10 for n and 4 for k, what do you get? 7. So we're saying follow that pattern clear until you get to 7. In this case, we're already done once we reach 7. Let's do one more example using a formula like this to make sure that you understand it before we move on to these. Let's say that we have 100 people in some group, and we're going to elect 10 of them to an office. So we have 10 different offices to fill. We have president, vice president, whatever. We'll call office 1, office 2, office 3, all the way to office 10. Okay? How many options do we have for the first person? 100. And we're going to keep doing this times 99, times 98, blah, 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 blah. When are we going to stop? What's the last number going to be? 91. She knows to stop from this formula. You do the number of choices you have, 100, minus how many choices you're making, 10, plus 1. So, 91. Which is exactly what you would have done if you didn't have that formula. You would have done, let's see, the first person there's 100, then there's 99, 98, 97, 96, 95, 94, 93, 92, 91. Oh, yep, 91. So yeah, you can count like that if you want, or you can look at the formula. Now, we do this so often that we have a notation for it, n sub k. Alright? So from here on out, this is not signifying, that's not a subscript for a variable. This is a formula. Just like you know something like n squared. When we put that 2 there, we mean 2 of them. When I do n sub k, what do I mean? I mean this. Good? That is shorthand for that formula. And you're going to want to know this formula, you're going to want to memorize this formula, you're going to use this formula all over the place. And I'm sure that the author brings it up again somewhere, I guess not in this section, but we have a special case where we have n times. So what is it when I have n times? Let's say I have 10 people and 10 offices to fill. So if I have 10 people and 10 offices to fill, how many ways can I do that?
1.
How many options do I have for the first office?
10.
10. How many options do I have for the second office?
9.
9. How many for the third?
8.
8. When are we going to end?
1.
1. So I'm going to do 9 times 8, or 10 times 9 times 8 times 7 times 6 times 5 times 4 all the way down to times 1. What is that? No, not what's the number. Have you guys ever seen this symbol before? 10 factorial?
No.
Oh, okay. I was working up to something thinking that we were going to make a connection here, but we're not here. You've never seen 10 factorial. Okay, then we'll cover it when the author brings it up. Never mind. My bad. Okay. So a couple more examples, and then we're done. So let's say that we have a bag with 3 items in it, right? I got my red marker, my blue marker, my green marker. We put them in a bag. Now, what are we going to do? We're going to reach into the bag, pull one out, and we're going to do that 5 times and record the result, right? So I might pull it out, and I might get, first we got red, then we got blue, then we got red, then we got red, then we got green. That could be one possible scenario, right? So, if I have an object, or if I have a bag with 3 items, and I select 5 objects from the bag with repeats, I pull it out and I put it back, how many possible lists can we make?
15.
3 to
15?
the power of 5.
Or 5 to the power of 3.
5 to the power of 3.
We can make a lot more than 15.
Yeah,
So,
5 to the power of 3.
how many options do I have for this one?
5. 3.
3. I have 3 options for this one, red, blue, or green. How many options do I have for this one?
3.
3. So for each of those 3 options, I have 3 options. For each of those 9 options, I have 3 options for times, which is equal to 3 to the 5. Okay. We have n objects that we're choosing k times. We have 3 items in a bag that we're choosing 5 times. 3 to the 5. Make sense?
Yeah.
Let's do another example. This time we're switching it up a little. This time we have a bag with 5 markers in it. And we're going to choose 3 of them without repeats. So once I pull it out, I can't put it back in. I guess we're off the screen there. I shouldn't write over there. I need to write over here. So I've got 5 objects in a bag. I pull one out, and then I pull one out again without putting my first one back, and then I pull another one out. How many ways can I do that?
5 times 4 times 3.
5 times 4 times 3. Now you could have counted down like that, or you could have used your formula. We start at 5, and we keep going until we get to 5 minus 3 is 2, plus 1 is 3. So from 5 to 3, 5, 4, 3. Yep. Understood?
Yeah.
How to use a formula? I know that's a really simple example where you're like, why would I use a formula? That was easy. Not all of them are going to be so small. So make sure the formula makes sense in how you use the formula to answer that question. Not just can you answer an easy question. You understand how to use a formula? You positive? Alright. And let's do one more. So this time, I have a bag with 3 objects in it. And I'm going to select 5 objects from the bag without repeats. How many ways can I do that? You can't. Okay, so we have a breakdown in this formula right here when k is bigger than n. If I have 3 objects, the most I can pick is 3. If I don't have repeats. So this formula only makes sense where k is less than or equal to n. So something like this, 3, and we're going to take 5 of them, makes about as much sense as 1 divided by 0. What are you talking about? It doesn't work. Okay? So the k has to be smaller than the n, less than or equal to. Otherwise, what are you talking about? Am I losing you?
I just can't you do, isn't it just one?
Isn't it just 1?
Yeah.
How many ways can I take 5 objects out of a bag with only 3 if I don't put the objects
I'm
back?
saying the 1 divided by 0. It's not just 1.
No, no, no. 100 times no. Look, let's pretend that 1 divided by 0 is equal to 1. Then multiply both sides by 0, and I get 1 is equal to 1 times 0.
Which is okay.
Yeah. Alright. So there's some intuition for why that's a broken thing to say. So that covers lists and some basic counting problems. So you'll be doing counting problems like this over and over again. Pretty simple. If you read the book, you'll get a way deeper understanding than just me up here talking. So that ends the lecture. And then we can start doing homework questions. Let's turn this off.